All right, the logistic model is the second major type of differential equation we're going to be solving. So this has a lot to do with the exponential models that we've been talking about. So just to recap some of that, with our exponential model, the idea is that the rate of change of whatever we're measuring, I'm going to talk about population, so dp dt, is always proportional to what the population is. If you have $100 in your bank account, that might mean that you're earning, your bank account is increasing at a rate of $2 a year. If instead you had $1,000 in your bank account, you're increasing at a rate of $20 a year. So if we continued this logic, if you had $1 trillion in your bank account, you're increasing at 20 billion a year. And for something like bank accounts, this might work, and you know, for any conceivably large number, this logic holds. However, this type of exponential growth crops up in other situations where we have a slight problem with the total carrying capacity. So one really common example is things like population growth. So if we moved and we settled some island somewhere, and the current population in that island is 100 people, then maybe this is a good model. Maybe after some amount of time, maybe after 20 years, we're up to 200 people, and after another 20 years, we're up to 400 people, and we can sort of keep going. However, at some point, the island's only so big. At some point, we're going to run out of real estate. So what this model says, when we have the solutions looking like our starting condition times some e to the kt, this means that it's going to just keep increasing. So it's just going to keep going and getting bigger and bigger and bigger. At some point, we run out of space on the island. So, or run out of food on the island, or what have you. At some point, this model has blown past some theoretical carrying capacity for the island. So what the logistic model does is it takes this limiting amount into account. We're saying that instead of our rate of change always being proportional to the population, our rate of change is going to be proportional to the population times, we're going to call this the percent, what do I want to call this? The percentage of remaining capacity. So while the population on our island is really small, the percentage of remaining capacity is big. This whole thing looks like an exponential. However, when we get close to being maxed out, since if we have a lower percentage of remaining room on the island, then this logistic model is saying that our rate of increasing is going to actually start decreasing. So this is going to help us, this is going to model this idea of the growth capping out at some higher amounts. Okay, I've been using the example of population on an island. Another very common example, especially in today's world, is the rate of change of, or the prevalence of some disease or virus. So right early on in a pandemic, if there is plenty of room for the virus to spread, then we're talking about an exponential growth. When we've got 10 people with the disease, it's going to grow at a certain rate. When you get up to 100 people with the disease, it's going to grow at 10 times that rate. But clearly this isn't sustainable, right? At some points, everybody's going to get it, or hopefully something sooner. This logistic model takes into account the idea that, hey, we're going to sort of start running out of room. There are going to not be enough different people for the disease to jump to. And this logistic model is an extremely fundamental or extremely simplified version of a model for something like this. Next week sometime, we're going to be talking about slightly more sophisticated versions of this that take more things into account. But this is sort of our first look at a model for something that is immediately relevant. Anyway, the idea is that so the fundamental idea behind a logistic model is that our rate of change isn't just governed by the population, it's also governed by how much room there is left in whatever we're talking about. So we're going to go through sort of how to solve this, or skipping over some of the pieces, but the solution that we get is always going to start off looking like an exponential, but then at some point it's going to flatten out and approach some limiting factor. So we're typically going to call this limiting factor L, and our solutions are going to look like this curve. So this is called a logistic curve, and it's going to end up being the solution to this particular differential equation once we fully set it up.